let's start. Okay, today we'll start the second term of the first section, which is electrotherapy. And we'll see one part of this section, which is waves. So in this second term, which is in the electrotherapy, we'll see the different kinds of waves. We'll start from the very beginning. So I will take you to your high school and bring you back. Then we'll see the basic electricity, how electricity is produced, how it transfers of conductors from one place to the other, then the different parameters or properties associated with this electricity. We'll see electrical currents. And we'll see also the principle of ultrasound and how it can be applied for therapeutic purpose. We'll see also the laser, the production of laser, and the different kinds of laser, their application for therapeutic purpose. We'll see also the shortwave therapy, or we call it the shortwave diathermy therapy. So electrotherapy is the use of electrical currents passed through the body to stimulate nerves and muscle in the treatment of various forms of paralysis. It can be also applied for treatments including the use of electrical devices such as deep brain stimulators to treat neurological diseases. The term electrotherapy, as the name implies, it is applying electricity to stimulate or to give pain relief to the body. Different kinds of electrical currents, as well as their associated properties, also can be used for therapeutic purpose. So starting from the electricity, ultrasound also can be applied, laser also can be applied, and different kinds of waves that exist that can be found on the electromagnetic spectrum also can be applied for therapeutic purpose. So we will see the basic definition of wave and the properties of wave. So you'll have insight about the different kinds of waves that can be found in the electromagnetic spectrum, and you'll see which part of the electromagnetic spectrum can be applied for therapeutic purpose. So let's start from the very beginning, which is wave. So what do you think is a wave? Okay. Any other? Yeah, the movement of particles transferring energy from one to the other. Any other definition? Can you give me some example of waves? Sound wave. Okay. Any other? Yeah. Infrared wave. Microwaves. Yeah. So wave is a periodic disturbance or rhythmic disturbance that carry energy without carrying matter. It doesn't carry matter, but it carry energy. It could use matter to transfer from one place to the other place, but doesn't carry matter. So it is a disturbance, a periodic disturbance or rhythmic disturbance that carry energy without carrying matter. It is also a means of propagating energy or information from one point to other point. There are different kinds of waves. There are different sources of waves. The signals that we get from, for example, our remote control, it is infrared. So this is one part of a wave. Wave also can be produced from vibration of materials. Wave can be produced from the sound, from when we speak, the particles will vibrate and they will carry the sound energy from one place to the other place by compressing and relaxing that materials. So waves can be produced from different sources, and they carry energy, but they don't carry matter, but they can use matter to transfer from one place to the other place. Generally, waves can be classified into two, depending on the use of the medium. One is mechanical wave and the other is electromagnetic wave. The mechanical waves, as the name implies, they require a medium to transfer or to move from one place to the other place, to carrying energy and transferring that energy. They require a medium. They can be also classified based on the movement of the medium and their direction. They can be classified into two, longitudinal waves and transverse waves. An example of longitudinal wave is the sound wave. The direction of the particle is the same as the direction of the wave in the case of longitudinal waves. But in the case of transverse wave, the direction or the movement of the medium is perpendicular to the direction of the wave or the movement of the wave. A medium is just a substance through which wave can travel. For example, air can be called a medium. Water that carries the wave is the water or ocean wave. Particles, a string is solid, liquid, gases. All of this can be considered as a medium for a wave. Other example of waves are electromagnetic waves. These electromagnetic waves propagate through vacuum without requiring any medium. They are consist of two kinds of waves: electrical waves and magnetic waves. That's why they are called electromagnetic waves. So lights, microwaves, infrared, X-ray, ultraviolet, radio waves, all the waves that are found on the electromagnetic spectrum are called electromagnetic waves. They don't require a medium to move from one place to the other place. So specifically transverse waves, the direction of motion of a particle is perpendicular to the motion of the wave in the case of transverse wave. So as you can see, this is the direction of the movement of the medium, and this is the direction of the energy. You will find energy at this point. It begins at this point, and you'll find the energy at this point. For example, when you swing a rope, the energy from one person will transfer to the other person. So this is the direction of the energy. But the direction of the medium is perpendicular to the direction of the wave. So these are called transverse waves, where the direction of the motion is perpendicular to the motion of the wave. So these transverse waves can be explained in terms of their amplitude, which is the distance from the stabilized point, or we call it the DC point, to the maximum, or to the peak point. It is called the amplitude. And the crest, which is the maximum point, the trough, the minimum point, and wavelength is the distance between two same phase points, or for example, the distance from one crest to another crest, or the distance from one trough to another trough. It's called a wavelength. This is the equilibrium position, or the average point, or the DC point. So these parameters can be used to explain the transverse waves. The other kinds of waves are longitudinal waves. An example, best example of longitudinal wave is sound. The direction of motion of the medium is the same as the direction of the motion of the wave. So, as an example, you can take the medium as, for example, the air. And when sound transfers from one point to another point, the particles will compress and relax when they transfer energy. So they can be explained in terms of the compression and refraction. This is compression part. where high energy can be found, and this is a refraction part where energy is released from this point and transferred to the other point. So the direction of the motion of the wave is the same as the direction of the motion of the medium in the case of longitudinal waves. So these kinds of waves can be explained in terms of compression and refraction. Compression is the highest point where the energy can be found, and refraction is the lowest point where the energy can be found. You can see also a spring as an example. The compressed part is called the compression. You can find high energy at that point, and the relaxed point is the refraction. So by compressing and relaxing, you can transfer energy from one place to other place, and the direction of the medium is equivalent to or the same as the direction of the wave. The second part of wave is electromagnetic waves, which do not require a medium to transfer. So electromagnetic waves propagate without a medium. They can propagate through a medium, but they don't need a medium to transfer. They can propagate through a vacuum. They can propagate through also a medium, but they don't require the medium. So they travel through a vacuum in free space at a speed of light, but when they propagate through a medium, the speed will decrease because most of the speed will be attenuated by the medium, and their direction also could be changed in the medium. So these electromagnetic waves, they are composed of electric field variations and magnetic field variations. That's why they are called electromagnetic waves. So an example of electromagnetic waves are visible light, X-rays, radio frequencies. Any waves that are found in the electromagnetic waves starting from the lowest frequency to the highest frequency can be called electromagnetic waves. Most of the applications that we found in medical they use these electromagnetic waves for either imaging purpose, for therapeutic purpose, or for diagnostic purpose. Electromagnetic waves are used in different forms. So this is the electromagnetic spectrum that you can find many different groups of electromagnetic waves. It is a continuous range of electromagnetic radiation from the long waves with a low frequency. That means from a large amplitude or high amplitude and lower frequency to a small amplitude and high frequency waves. You can find different forms of electromagnetic spectrum waves. So the radio frequency, you can start from the radio frequency, which is a lower frequency waves that you can find in the electromagnetic spectrum. Then there is the microwave, infrared, visible, ultraviolet, X-ray, and gamma ray, which is the highest frequency and lower amplitude electromagnetic spectrum wave. As an example, ultrasound can be used for therapeutic purpose. Infrared can be used for therapeutic purpose. Among these electromagnetic spectrum waves, the shortwave, microwave diathermy, and shortwave diathermy, that is the frequency difference, can be used for therapeutic purpose. Therapeutic ultrasound in lower frequency also can be used for therapy. Higher frequency, lower frequency can be used for therapeutic purpose. There is also transcutaneous electrical nerve stimulation, or call it TENS. It can be used for therapeutic purpose to stimulate surface skin or nerves that are found on the surface of the skin. So there are different kinds of applications that use the electromagnetic wave for therapeutic purpose. Not only for therapeutic purpose, they can be used also for diagnostic purpose. For example, the radio waves can be used in MRI to create imaging to find any malfunctioning structure in our body. Ultrasound imaging is one part of diagnostic imaging technique that uses ultrasound waves. X-ray projection radiography or computer tomography, they use X-rays that are found in the electromagnetic spectrum. Gamma rays, positron emission tomography, or we call it PET, they use the gamma radiations to detect the body malfunctioning structure. Gamma rays also can be used for therapeutic purpose in radiotherapy, for example. In the radiotherapy, the cobalt-60 machines that produces the gamma rays, they use these gamma rays to kill any tumors that are found on the brain or any part of the body. So these electromagnetic waves can be used in different forms for therapeutic as well as for diagnostic purpose. So let's see the properties of wave as it propagates. When a wave propagates from one place to other place, if it interacts or it passes through a medium with a different boundary or a different density, it can be explained into two forms, like reflection and refraction. When a wave is reflected, it's bounced off from a surface, and the amount of reflection and refraction is dependent on the property of the surface, or the loss of intensity is dependent on the surface or the difference of density between two mediums. So two properties can explain the wave propagation, reflection, and refraction. There are two kinds of laws of reflection and laws of refraction. So in the reflection, there is a normal surface which is drawn perpendicular to the reflecting surface. This is the reflecting surface. This is the normal line which is perpendicular to this reflecting surface. When the incident radiation interacts with this normal surface, it will reflect it back, and the law of reflection says the angle of incidence is equivalent to the angle of reflection. So theta 1 is equivalent to theta 2. So this is the law of reflection. You might remember from your high school class, I think you studied it. The second law is the law of refraction. When a wave undergoes refraction, as it passes from one medium to another medium, it will bend, or the line will be broken, or the direction of the propagation will be broken, because the energy, some amount of the energy will be attenuated on the medium, and the energy will decrease, as well as the direction also will change. So the law of refraction says sine theta 1, which is the angle of incidence with respect to this normal line, divided by sine theta 2, which is the angle of refraction with respect to this normal line, is equivalent to the refractive index of the medium, N2 or N1. N2 is the refractive index of this medium, N1 is the refractive index of this medium. So these refractive indexes, they give information about the property of this medium, how much they can bend the incident light, how much they can attenuate the incident refraction, wave. They can give us information about this angle of, index of refraction, refractive index or index of refraction. So when a medium have high density, the index of refraction also will be high. So it will attenuate the incoming wave, and the direction also will be changed or bent over. So n can be found by dividing the speed of light with the speed of light on the medium. So if the medium have high density, the velocity of the incoming wave will decrease on this medium. So the angle of, the refractive index will be higher. So the angle of this refraction also will be different depending on the refractive index of the medium. So different medium have a different index of refraction. For example, vacuum have just one index of refraction. That's why the speed doesn't change, the speed of fluid doesn't change when it moves in the vacuum. So using this formula, if n is equivalent to 1 for a vacuum, if n is equivalent to 1, the speed of the wave on the vacuum will be the same. C and V will be the same. So the speed of light on the vacuum through the vacuum is 3 times 10 to the power of 8 meters per second, right? So the refractive index for vacuum is 1, for air 1.0029, water, ethyl alcohol, sugar solution, it will increase as the density increases. So it's called the Snell's law, or the law of refraction, which is sine theta 1 over sine theta 2, which is equivalent to n2 over n1, or n1 sine theta 1 equivalent to n2 sine theta 2. So you can find the angle of refraction if you are given the medium, as the medium is, and if you know the angle of incidence. So this formula is used to describe the relation between angle of incidence and refraction. It's the Snell's law. Let's do a simple exercise. Let's assume you are applying infrared light treatment to a client. If the light source is applied to a 20 degree to the normal, you are asked to determine the angle of refraction in the patient given the refractive index in the air is 1 and in the tissue 1.33. So the boundaries are there is air and there is a tissue, and you send infrared light to a tissue. Okay, that's simple, right? So you can assume this as the boundary between the air and the tissue. So the refractive index of the tissue is equivalent to 1.33, and the refractive index of air is equivalent to 1 for this case. So the infrared wave or light is applied 20 degree to the normal, so this is the normal. The normal line is the line which is perpendicular to the surface. So this is applied in this direction. So theta 1 is this one. So theta 1 is 20 degrees, right? So you are asked to calculate the angle of refraction as the light passes through the tissue. So this is theta 2. So it could move this way or this way. That will be determined by theta 2. So using the Snell's law, sine theta 1, n1 is equivalent to n2 sine theta 2. So the unknown variable is theta 2, which is equivalent to n1 sine theta 1 divided by n2 so n1 sine theta 1 divided by n2 will be equivalent to sine theta 2. So theta 2 will be equivalent to sine inverse of n1 sine theta 1 divided by n2. So after calculating this one and taking the sine inverse, you'll find theta 2. So this is around 40.9 degree. So the direction changes toward this normal line. So theta 2 decreases. So the some part of the infrared light is attenuated on the tissue, and that infrared is absorbed on the tissue. That's the aim of its application also. After it is absorbed by the tissue, it will stimulate or heal any pain that the tissue may have. Okay, let's see some pointers about wave, analysis of wave. As a wave propagates from one place to the other place, it can be explained in terms of two variables. It's dependent on two variables. If there is a function, that function will be dependent on other independent variables. So the two independent variables for a wave are the position and time. As the wave propagates, it will propagate through space. That means the position where the wave will be at time t equal to 0 will be different at t equals to some value. So it is dependent on two variables, position as well as time. So it can be explained in terms of a function which is y equivalent to f of xt, where y is the amplitude of the wave at position x and time t. So by disintegrating this function into two, we can see this wave as a function of position only and as a function of time only. When we explain or when we draw the wave as a function of position only, we'll find the wavelengths and other parameters. And when we draw this function in terms of time, we'll find the period t, or we'll define the period t. So the wavelength is the distance between two same phase points. The two same phase points as it propagates through this position. So the distance between this point and this point can be called the wavelength, or if you are taking initial point this one, the next point will be this one. So the distance between this and this will be a wavelength. So wavelength is the distance between two same phase pointers. And period, it is the same, but it can be found when you draw the function in terms of time t. So the parameters that we saw before can be expressed in terms of this function or analysis of wave. Amplitude is the distance between the equilibrium point to the maximum point, or in terms of the lower point also you can explain it. It is equivalent to the maximum point minus minimum point over 2, which is the distance between this and this. Wavelength is the distance in meters between two successive pointers or two same phase pointers. This is the wavelength. If you take the initial point, this one, you will search the same phase point, and the distance between that point will be wavelength. Period, it is the time separation in second between two successive pointers of the same phase. This is the time separation. This is the distance or position separation. Frequency is the number of waves passing a point per second. It's expressed in terms of per second or hertz, and this is equivalent to the reciprocal of period. F is equivalent to 1 over t. These are the basic definitions. Velocity, it is the velocity of propagation, either through a medium or through a vacuum. It is explained in terms of meter per second, and velocity is equivalent to frequency times the wavelength f times lambda. So these are the basic parameters that are used to explain waves. So as an example, just you can do this exercise. Red laser has wavelengths of 632.8 nanometer. You are asked to determine the frequency of the wave. The second example, assuming that sound travels at 330 meters per second in the air, determines the wavelength is of the notes middle A, which you can find on the piano, which has a frequency of 440 Hertz. Okay, then the first example, the wavelength is given for the red laser light, which can be applied to stimulate skin for cellular rejuvenation to increase the blood flow. So red laser light have a wavelength of lambda, which is equivalent to 632.8 nanometer. And you are asked to find the frequency of the wave, assuming that it travels with the speed of light in the vacuum. So the V frequency, the speed will be equivalent to 3 times 10 raised to 8 meters per second. Then using this formula V, which is equivalent to the wavelength times frequency, you can calculate the frequency F, which is equivalent to V over lambda. On the second example, the speed of sound is given, which is V equivalent to 330 meters per second, and the frequency F is equivalent to 440 Hertz. So you are asked to determine the wavelength is lambda, which is equivalent to V over F. So for the first example, the frequency will be 4.74 times 10 to the power of 14 Hertz. And for the second one, it will be 0.75 meters. So in the next class, we'll see the interaction of one wave with the other wave and the different properties of waves. That's enough for today. If you have any questions, please welcome.